Mr. Chairman. So, I will try to briefly describe the work entitled The Influence of Friction on Delamination in Fiber Reinforced Composites and Symmetric Galerky Boundary Element Implementation, which has been made in collaboration with my supervisor, Professor Composites. So, the presentation has been divided in the following parts. The first, introduction. I will try to explain our motivation and objectives of our study, following the concept of the fibermetric interface model, interface damage, and formulation of the frictional contact at the interface. Also, numerical solution and computer implementation. And finally, I will try to briefly describe some numerical example where the previous items have been applied. So, about the motivation, recently the phenomenon of delamination at composite materials in combination with effect of friction are really challenging. The present study discusses the delamination and the fibermetrics composites, and our contact model is presented for a mathematical point of view using such a cohesive interface model, taking into account the possibility of frictional contact at the interface, and also the whole system is implemented in the symmetrical boundary element code. So, objectives, we are focusing in our work to the crack investigation, crack onset, and crack propagation of the fiber reinforced composites. And it is necessary to mention that the whole system is governed by the energetic concept which has been proposed by Robichek et al. So here we can define the interface damage model. At the picture we can see the concept of the interface bonding. You can see matrix and inclusion, fiber inclusion. And what is really important to say that at the interface between the matrix and the fiber, the standard signorini condition of unilateral contact have been replaced by the normal compliance finalization condition, where we can define, the relative negative part of the relative normal displacement, and also the term kg, which corresponds to the really high normal stiffness, which allows some penetration at the interface. So let's continue. Formulation of the frictional contact. What is really important to say that our model assumes a classical Coulomb friction law with a constant friction coefficient. And as I said, that the system is based on the energetic solution. It is really important to define energy stored in the bulk and at the interface and energy dissipated due to the friction, which is represented by the following integral, where we can see the term f zeta, which corresponds to the friction function, which designates the activation of friction with respect to the decreasing interface stiffness. So as you can see, the damage parameter zeta 1 corresponds to the perfectly bonded interface. At the time when zeta starts to decrease, friction functions start to increase until it reaches the friction coefficient. So it's the implementation of friction model. So here we can see the interface damage model. On the left side, we can see the classical formulation of linear elastic brittle interface model, which yields a classic scenario that assumes really discontinuous response of the mechanical stress in tangential direction, and also the damage parameter zeta with the dashed blue line and the friction function dashed red line. However, in engineering application, another approach is really preferred, assuming such a continuous response of the engineering parameter of the interface parameters as the fractions, and also the damage parameter, assuming some softening stage at the damage evolution part. The following concept has been achieved by adding additional term including zeta squared and additional stiffness terms in an energetic formulation, as you will see. Also, it's really important to mention that the crosshatch area, the blue, represents the energy dissipated due to the interface damage, and the red, energy dissipated due to the friction. So, energetic solution or energetic formulation is governed by the following system of nonlinear inclusions, which can be also replaced by the energetic solution, where we have to define energy stored or the functional, energy stored functional of the bulk with the blue color, and also energy functional or stored energy of the interface with the red color. As we can see, here are the additional terms which we have mentioned in a cohesive formulation, and also it's necessary to define the potential energy of the external forces and dissipation potential. Also here we have the energy dissipated due to the friction and energy dissipated due to the interface damage. Okay, the mentioned functionals has to be summed in the total energy functional, as you can see, HK, for any visible displacement U, and satisfying the condition that also zeta is decreasing, has a decreasing character. So the interface is always diminishing. Okay, description of the model. The non-convexity of the functional total energy functional H requires applying a special numerical treatment in the minimization procedure. So we have used alternative minimization algorithm that achieve to use the convex quadratic functional or quadratic programming algorithms. So here we can see the layout of the tested numerical sample. You can see the geometry of the fiber composite specimen that has been taken from the work of Navarra, and also spherometric composite specimen, which contains 10 infinitely long fiber inclusions that has been loaded on the top and on the bottom side by tension load. Here we can see the model properties of the fiber and the matrix. Young's modulus stiffness parameters of the interface for the cohesive interface model, which we have to split in these two terms, and also the parameters that govern the crack growth, the fraction energy, and the Coulomb friction coefficient. I have to mention that the whole procedure has been made 3 times, so we have investigated the same layout for a friction function 0, 0.5, and 1, because to capture the influence of the friction and the fibermetric interface. So here we can see some evolution of the crack propagation. The evolution of the crack propagation started for the fiber 5 first time at the low step 105. At this location, you can see the crack propagation. It was governed by the energetic solution, where when the traction achieved the critical value of the normal stress, and also here we can see the decreasing character of the damage parameter zeta on the right side, and also decreasing character of the traction normal and initial tractions up until the total breakage of the interface has been occurred. And here we can see the influence of the friction at the fiber 5 for the whole 3 models at the low step 120 for the model with friction coefficient 1, 0.5, and 0. Let's focus on this area where we can see that the normal tractions acquire the negative values in the whole 3 models, and the damage parameter zeta starts to decrease. It's not completely damage the interface, but starts to decrease. So here we can see that interface can transfer some shear forces for the model with friction coefficient 1. However, for the model without, you can see any. So that's what I wanted to present. Also, then we can look on the interface deboning. Also, we can see the another location of the upper tip at the fiber number 4. So here we can see that the friction effect can slow the process of the interface damage. And finally, I wanted to show some deformations corresponding to the 4 different load steps for the cohesive model with friction coefficient 1. The process started at the fiber number 5. Here we can see it, and this is the last load step. So, conclusion, an energetic-based model for solving the contact model of fiber-reinforced composite with effect of friction has been discussed, and obtained results confirm the influence of the friction during the damage process of the interface. So, thank you for your attention.